Hello, welcome to this video. So I actually got the setup of a face cam, so uh, the videos will feel a bit more interactive. Uh, but let's jump in for what we're here for today. So today we're going to look at why the area between a curve above the x-axis and the x-axis, so something like this, from A to B, and by the area under the curve, between the curve and the x-axis, I mean that we draw perpendiculars to the x-axis from this A and this B. I'm referring to A and B as the x values for these 2 points. So, the area would be just the area bounded by all of this. So this curve, these perpendicular lines, and the x-axis. So all of this. And we will show why that is equal to, if this function is called f of x, then the area would simply be the integral from a to b of f of x dx. Now, if you already know what an integral is and don't want to recap, just skip through the video. But for now, let's begin a recap. So the first thing we're going to do is to look at just an integral without any bounds. So this would be, we'll call this big F of x plus a constant c. So c can be any number, 1, 2, 3, negative pi, 0.0001257, 9, 10, if that makes sense. Whatever you want. But just a regular number. No expressions of x or something. It can be a variable as long as it's not something with x. Now, big F of x we will mark as the past function of f, small f of x, meaning that the derivative of big F of x will be small f of x. Okay, now let's do a nice quick example for this. So let's do the integral of 2x dx. So what we want to do is to find a function such that its derivative would be, 2x. So let's see. Now, because we have just an x, and remember this is also x to the first power, we might want to look at derivatives of powers of x. Because remember, if we have the function x to the n, its derivative will always be n times x to the n minus 1. And because if we look at from the derivative to the original function, the power of x, if we ignore the constant, would grow up by 1. And because we have the power of 1 here, and we want to find the past function, we might consider looking at the function x squared. So, because obviously 2 is bigger than 1 by 1. And if we take the derivative of f of x, so remember the 2 hops to the front, and it'll leave behind a minus sign with the 2. So I'll have 2 times x to the 2 minus 1, and its 2 minus 1 would give 1, so x to the 1, that's just 0. X to the 1, I mean that's just x. And would you look at that? We're lucky enough to find that the exact thing, the exact derivative of x squared would be 2x, which is our actual function. Meaning that our solution to this integral would be x squared plus c. And by the way, this constant c catches on because the derivative of any constant function, y is equal to 1, y is equal to 3, is equal to negative 5 over 4.7, the derivative of that will always be 0. Meaning that taking the derivative of this to get this function, this plus c, will just be like nothing. Its derivative would be 0, so it won't do anything. Which is why there are actually infinitely many solutions for this integral, which are all apart by just a constant. Uh, so yeah, that's it for these more simple integrals, can say. Now let's go look at integrals with actual bounds. Okay. So now let's look at this kind of integral with bounds a and b. So this is very simple. Again, we will define the path function of the small f as big F of x, being that the derivative of big F of x would be small f of x. And so this integral will give you big F of b, the upper bound, minus big F of a, the lower bound. And now you might be wondering, but aren't there infinitely many uh, ways to have the path function for f of x? Doesn't that mean that I'll have infinitely many solutions to this integral? Does that mean that any constant is equal to any other constant? Well, no. Okay, not exactly. Here's the deal. Although there are infinitely many uh, functions, uh, infinitely many path functions for every function, remember that they're all separated by a constant. So when we subtract value of b from value of a, for example, the constant, whatever we attach, 1, 2, negative 5.32 times pi, that would just cancel out because we subtract that constant. And you can easily see why. If you want to see it algebraically, then you'll see it yourself when you write it down. Okay. So that'll mean that uh, we'll just have to choose just one past function, doesn't matter which one, and we'll just plug it into this formula and get a single constant value for this interval. So let's do a quick example of this. So we'll have the integral from 0 to 1 of 2x again. This time we have bounds. So remember that the antiderivative, or the integral of 2x, the path function of 2x, will be x squared, which we just derived. So what we will do is take that x squared and have it go from 0 to 1. And this is how we will write it. Square brackets, 0 on the bottom right, and 1 on the top right. Like this, instead of bottom left, bottom left and top left on this interval. And then all we have to do is this. Have 1 plugged into this x squared to give you 1 squared, or 1, and then you subtract it from uh, 0 plugged into here, which is 0 squared, which gives you 0, which is 1. And that'll be the just simple constant solution for this interval. Okay. that's pretty much it for integrals with bounds. Again, I'm doing a pretty simple recap. There are a bunch more things to integrals that just I don't have the time to go over. But you can check those yourself. Or if you want to, I'll make a video entirely about complete integrals and everything you can do with them. But that's pretty much all we'll have to know for this video. So now let's jump into our actual goal. Okay. Now, here's the thing. This area looks very, very complicated. Like, how do we even start measuring it? Well, let's try look at simpler shapes. Let's look specifically at a rectangle. A rectangle has a very neat way of measuring the area. Take the sides, uh, neighboring sides, so say this A, and this is B, and the area, which we'll mark as S, would give you, and S is equal to A times B. Very neat. And you can even have multiple rectangles stitched together and easily find the area by splitting it up into rectangles, finding each area individually, and then summing it all up. So let's do an example here. So uh, let's let's see. We will call this, and we'll say that this length is 2, this length is 1, and this length is 1, 2, and this length is 0.5. So our area would be, by splitting up into rectangles, would be the area of this rectangle, 1 times 0.5, which is 0.5, plus the area of this rectangle, 2 times 1, which is 2, which gives you 2.5 as the area of this shape, which before doesn't, which doesn't actually have a nice formula for it, but it can be uh, easily found, and the area can be easily found by just splitting it up. So we might be able to use this sort of trick uh, to our advantage in this problem. So here's what we're going to do. We are going to split it up into some rectangles. So we'll have this as a rectangle. We'll have, and then we'll take this as a rectangle. And I'll take this as a rectangle. Now, summing up the areas of these rectangles, will give the area of the shape that we drew. Now, won't be the area of, it will not give you exactly the area of the function we're trying to find, because you see there are all of these holes. So it's an approximation. But we can fix that by just adding more rectangles. Okay, so let's do thinner rectangles. How about this thin? Uh, and we'll do, just for simplicity, we'll do all of the widths being the same thing. That will be a bit useful for later. Okay. Okay, so now we have 5 rectangles instead of 3, and you can see that our gaps are now smaller. So this will give us a better approximation for the area. And what we will in fact do is completely let that area, let the the amount of rectangles or the width of the rectangles approach zero, so the amount of rectangles approaches infinity. Now, we can say that uh, the widths are exactly zero, so we'll have infinitely many uh, rectangles with width zero. So we'll get the problem of infinite rectangles with area zero, which uh, is an indeterminate form. So let's see. Okay. What we will do is instead let the width approach zero. We will let it be a very small number that is very close to zero. And so we'll end up with this kind of thing. Again, I'm a bit exaggerating, but uh, you can imagine in your head a bunch of very small rectangles with their widths getting smaller and smaller and their mouths getting bigger and bigger until it almost exactly fills our area that we are trying to find. Okay, so let's see. Now, we will let their widths be h, and that will mean that we're essentially letting h approach zero, which is a limit. So let's write it here. That will give us the limit as h approaches zero of what? Well, the area of all these rectangles, uh, which as uh, goes closer and closer to zero, uh, will give us a better and better approximation for the area. So let's do this. And this is where uh, the fact the entire function between those bounds is above the x-axis comes in handy, because then the height of the rectangles will just be the values of their function. So for this one, we will have, for this first rectangle, we'll have the width being f of a. So this is the thing that we have. We have f of a and then times the width, which we defined as h. Okay, next rectangle. Because the widths, again, are all h, the x value of the next point, which we have the second rectangle from, would be a plus h, meaning that the next rectangle would have an area of f of a plus h times h. Again, because the height of the rectangles will just be the value of the function. And so on, we'll have f of a plus 2h times h, and so on until we end up with f of b minus h times h. And it's f of b minus h times h and not f of b minus h, because at our last rectangle, as you can barely see it, but here's the last rectangle, the point that uh, gets us the actual rectangle is the point behind b, which is b minus h. The point b doesn't actually have a rectangle uh, from it. So it'll just end at f of b minus h times h. Now, let's look back to our derivative. So, let's see. F of x is equal to the limit as h approaches 0 of big F of x plus h minus f of big F of x all over h, and big F is the past function for small f. So the derivative of f is equal to small f. And so we will just plug in each f of something into this. And and because we already have the limit as h approaches 0, why won't we just let all of these h's be the same and just have it be basically the same limit? And we will end up with the limit as h approaches 0 of h times all of that stuff that we'll soon write. But then remember that all of these will have divided by h. So we'll take that out and have divided by h. And I'll take all the h out of this sum too. And as you can see, h divided by h, that cancels. So we just have what's in the sum. So let's see. For x is equal to a, we have big F of a plus h minus big F of a. For the next one, we have big F of a plus 2h minus big F of a plus h. And that will continue on until we have big F of b minus big F of b minus h. Okay, now let's see what we end up with. So in our sum, here's what we have. So we have f of a plus h, or big F of a plus h, minus big F of a plus h. So they'll cancel. Somewhere here we'll have negative big F of a plus 2h, so they'll cancel with that. In fact, all of these terms will cancel, and this will cancel too, because behind it there's also going to be that term of big F of b minus h. And all we're left with is big F of b and negative big F of a. So we have this as being big F of b minus big F of a. And I didn't write limits as h approaches 0 because we don't have any h left. So now let's see. Okay. F of b minus f of a. Because f, big F, is the past function of small f, our original function, we know that uh, they'll pretty much by definition will be the integral from a to b of the original function small f of x dx. And that's it. A more algebraic proof of why the area under a curve above the x-axis will be just the interval of the function of that function that represents the curve, and obviously, of course, between those bounds. And that's pretty much it. If you want more content like this, please subscribe to my channel. I'll be uploading more stuff like this in the future. And finally, that's it.